Okay, guys, here we are back for, again, it's not going to be a long lesson, continuing on in chapter 7. Okay, here's some jokes for you. What did one hammer say to the other hammer? I broke a nail. Well, that was not bad. Why was there thunder and lightning in the lab? The scientists were brainstorming. And what did one candle say to the other candle? Let's go out tonight. So there you go. There's your jokes for this Monday. Okay, so what we're going to do, just real quick, kind of a glimpse, and I'm probably just going to do the slide I actually ended with on Friday and kind of go more in depth on that. But what we did in first year chem was we looked at the periodic table. We did this before the virus hit last year. We did this like in late January, early February. But we talked about periodic trends, and we compared the upper right-hand side of the periodic table to the lower to left. And we talked about being able to predict properties like ionization energy, electronegativity, atomic size. That's what we did in first year chem. And we said, okay, here's 2 or 3 elements, arrange them from the lower to the higher ionization energy. Well, we're going to do that again in regular chem, or in AP chem, I should say, but we're going to extend it just like they always do in AP chem and explain why. Why does this element have a higher ionization energy than that element? Or why does this element have a smaller atomic size than that element? So that's what we're going to do. And so I actually was looking at that, and I added a note or a page of notes, which is not online. So this would be something that you'd want to write down or take a picture of. So let me go back to where we were. Just a second here. Sorry for Mr. Wood and his technology problems. Okay. Okay, so it's this slide right here. So let me just talk through this. Okay, so again, like I said, first we're going to predict periodic trends, and we're going to really compare the upper right-hand side of the periodic table to the lower to left. But then we're going to explain. We're going to have to go and explaining. And that's why this test coming up is not going to be a lot of math, a lot of calculations. It's going to be way more on a lot of predicting or explaining or doing electron configurations or quantum numbers like that. Okay, but first of all, Coulomb's law, force of it, and like I said in class, one term that AP loves, and we're going to come to this actually, I think in chapter 10, so probably in late January, February, called Coulombic Attraction. The force of attraction between charged particles depends on, and think of the planets and the sun, the magnitude of charge. The greater the charge, the greater the force of attraction. So you have a big body like the sun. Well, if you have another big body like Jupiter, those two big bodies would have a bigger attraction for each other. The charge increases, force increases. And what we'll talk about in chapter 10 is we'll compare an ion that has a positive, or an ionic compound that has a positive 1, negative 1 charge versus an ion that's got a positive 2, negative 2 charge. And we'll say at that time that the combination with the positive 2, negative 2, because there's a bigger charge difference there, has a stronger force of attraction or a stronger Coulombic attraction. And then really more for us, but the distance between the charge. So the greater the distance between the charges, the smaller the force between the charged particles. And so what that's going to do for us, especially on B, down a column, we look down a column, those electrons are getting further from the nucleus, so they're going to feel less nuclear pull, thus they're going to be easier to remove, and they're going to make a bigger atom. Okay, so and I'm going to try and explain these briefly today, and I'll come back and do this again on Tuesday. But across a period or a row, this thing called ZEF, which stands for effective nuclear charge. And ZEF is equal to Z, the atomic number, minus S, the inner core electrons. And I'm going to do some examples. But this is as we go across a row. So we go across a row. The ZEF is going to increase. That means that the nucleus is going to have more of a force on the outer electrons. And then shielding decreases. And really the way that I'll accept, as well as the way AP will accept it, I think, as we look at elements across the row, you can use one or two things or both. The Zeph increases, shielding decreases, which means that as we go across the row, these nonmetals up here, their outer electrons are held together, are held tighter by the force of the nucleus. And I want to do some examples here on the board. So that's across a row. So the outer electrons are feeling more of a pull from the nucleus because there's less shielding. And again, I'll try and explain that. Down a column. But down a column, this does not have to do with Zeph at all. This has to do with that as we go, like we'll do lithium versus sodium versus potassium. So lithium is 2s1, its outer electron, sodium 3s1, potassium 4s1, so on. Well, as I go down the row, the distance from the nucleus is increasing. And so the force, just going back up to number 2 on Coulomb's law, the force is less. And then when an atom becomes an ion, you want to look at the proton-electron ratio. It's hard to read that, but as the ratio increases, the force on the outer electrons increases. And as the force decreases, there's less force on the outer electrons. So that should read, the bottom one should read, when becoming an ion, proton-electron ratio, as ratio increases, more force on the outer electrons from the nucleus. When it decreases, less force on the outer electrons. Okay, so let me just try and do a couple of examples here on the board, and that'll be it. I'm not going to do too long a lesson today. Okay, so the first one in the notes, I'm on point A, was this Zeph thing, across a row. So if I'm going to do the third, so I'm going to do the third row on the periodic table. So I'm going to start off with sodium. So the Zeph, which is going to be Z minus S. Okay, so for sodium, its atomic number is 11. That's what this is. And this is the number of inner core electrons, which if we did the electron configuration for sodium, it'd be 1s2, 2s2, 2p6, 3s1. So its inner core electrons are 10. It's the 2 plus 2 plus 6 is 10. So its Zeph is 1, which means if I try and make a visual of that, I have 11 protons in the nucleus, and there's 10 electrons here shielding this one electron. We always, when we're doing this, we're always looking at the nuclear pull on the outermost electrons. So these, it's pretty equal. We have 10 protecting from 11. So that electron is pretty well shielded. And that's what I mean by shielding. The inner core electrons, they like absorb the pull of the nucleus. Again, football is a good example. It's like you got 10 linemen blocking 11. Well, that outer electron is pretty well protected. Well, compare that to magnesium. So magnesium Zeph is 12. Its atomic number is 12, and it still has 10 inner core electrons. The magnesium, again, is 1s2, 2s2, 2p6, 3s2. So again, there's the inner core electrons. So its Zeph is 2, which means that the nucleus, that Zeph means effective nuclear force, so that this time the nucleus has a little bit more of a pull. And if I diagram that, I have 12 protons, 10 electrons, and 2. So now these 10 blockers, or 10 shielding forces, are having to protect from 12. So they're a little bit more outnumbered. So these outer electrons are not quite as protected. And that's, again, the Zeph here is 1 for sodium. So the effective nuclear force is 1 for sodium. It's 2 for magnesium, so it's a little greater with magnesium. Okay, so then I'll go, let me just go on to silicon. So I'll skip aluminum. So silicon is element 14, so its Zeph would be 14 minus 10. So silicon would be 1s2, 2s2, 2p6. So there's the inner core electrons, 3s2, 3p2. Those are the outer shell. Okay, so I've got 4. So this means this Zeph, the nucleus has a stronger pull. Well, if I diagram this, now I have 14 pulls. I still have those 10 shielding forces. That's what these are. And they're protecting force. So these electrons are not as protected. They're going to feel more of a pull from the nucleus. So you're seeing the pattern here as we're going, and you could write this on your periodic table, as you're going across the row, the Zeph is increasing, the shielding is decreasing. There's less shielding here. There's not as much protection. Okay, then if I do sulfur, so sulfur is 1s2, 2s2, 2p6, so there's the inner core electrons, then it goes 3s2, 3p4. So the Zeph here is 16 minus 10, which is 6. So even a stronger force from the nucleus. And if I diagram this to try and give you a visual, so again, now I have 16 poles that are going after 6, and now we're getting outnumbered. Okay, and if you think about this, up here in sodium, I had 10 electrons shielding or absorbing a pull from 11 protons, pretty much close to 1-to-1. Gets to be a little bit more lopsided, and now it's really getting lopsided. So again, so as we're going across a row, the Zeph is increasing, the shielding, again, across the row is decreasing. Simply meaning the electrons, those inner core electrons, are being more outnumbered. And then chlorine, so chlorine, the Zeph would be 17 minus 10, which is 7. So even a stronger pull on the nucleus. So if I diagram that, I'd have 17 protons, 10 electrons as the shielding. This is the shielding on these 7. So again, they're feeling even a stronger pull on the nucleus. What that means, as we go across a row, we're saying the effective nuclear force is increasing. So these outer electrons on these elements, these nonmetals, are feeling more of a pull from the nucleus, which means they're going to make them smaller. They're going to pull those in. They're going to make them smaller, and they're going to make it harder to remove these outer electrons. Okay, so that's what I was talking about with Zeph. Okay, now down a column. So B, I said down a column. So if we're comparing, so let's do, so here was point B. So I said as you go down a column, the the nucleus is going to have a weaker pull on the outer electrons. The nucleus and the outer electrons are getting farther apart. Getting further apart, so thus there's a weaker pull. So there's a weaker pull of the nucleus. On the outer electrons. Okay, so for an example there, so going down a column, there's a weaker pull by the nucleus, weaker pull on the outer electrons. So if I compare then lithium, which is 1s2, 2s1. So if I've got the nucleus, then I've got 2 electrons here, and I've got 1 here. We'll compare that to sodium. So what I'm talking about now are elements that are in the same vertical column. Okay, so sodium is 1s2, 2s2, 2p6, 3s1. Well, now this outer electron, again, we're always looking at this in terms of the very outer electrons. So if this is the nucleus, so now I would have 8. Actually, I have, this is what I have. I have 2, then I have 8, and now I have 1. But the point is now that electron is further. It is further from the nucleus, so it's not held as tight by the nucleus. It's getting further away, just like Neptune and Pluto are further from the sun. They don't feel as much pull from the sun. If I did potassium, it's 1s2, 2s2, 2p6. Again, a lot of these things, if I can do the electron configuration, it really helps me. So what I have here, this N is the nucleus, so I have 2, and then I have 8. And then I have 8 more, and now that outermost electron, even up here, when I was talking about Zeph, I'm looking at that outermost electron. It's getting further from the nucleus. So as we go down a column, the outermost electron is getting further from the nucleus, so it is held together, or it's held by the nucleus weaker as it goes down a column. Okay, I'm going to stop there. I'll come back and talk about the proton electron charge and kind of review this. It's definitely a little bit confusing, but if we can lay the groundwork, I think it'll help us for getting to the last part of the chapter. Guys, have a good one. I will see you on Tuesday. Remember, extra credits due by Tuesday.